So it's our pleasure to welcome Katerina Papagiannouli for the next talk.
Thank you very much. It's a great pleasure for being here, although it's a bit sad because Sayan is not around us, and this is a joint work with Sayan Mukherjee and Yang Baek. It started with this work started. These works started with Sayan when I was doing my postdoc at Max Planck Institute. So today I will talk about, again, my name is highlighted only because I'm here. Today I will talk about Bayesian nonlinear inverse problems, problems which are arising from PDEs. And I will try to do try to convince you why it is important to work with this type of problems that are arising from PDEs, and we will do some coverage and frequentist coverage, and we will see at the end some new directions that we are trying to work on recently. So my talk is divided in these four parts. In the first part, I will talk about, I will do some introduction on statistical inverse problems for PDEs. Then I will show you some results that we had recently on frequentist properties using Gaussian process priors. And then another work that is about to finish, what happened in these models when we have a misspecification, how we can extend these results in a model specification case. And at the end, I will show you some possible extensions, using this method the method that we developed for the frequentist part using the Gaussian process, what possible extensions we can have. And I will show you also some what are our future ideas and what we would like to see in this direction. Okay, so let's start with the introduction and what is an inverse problem. So when we get our data are noisy observation, and basically we need to identify there some parameters the most of the times. So the inverse problem actually tries to identify this hidden information which is in the data, and we would like to uncover. So in this particular example, and in this particular talk, we will see problems which are arising, inverse problem which are arising from a PDE. And so, for example, we have noisy data, and we would like to do a PDE, and we would like to uncover and estimate some unknown parameter of the PDE. Okay, the typical observation scheme is that we get from our data is the following. So we have a conductivity field and or diffusivity field, and it's constant. Then we have some advection field, and then at the end we put some source function, and then we have our mathematical model, which is a PDE. So the noisy free solution will be given by this plot, but what we observe is this one. So from this one, we would like to do some to identify some parameters of the PDE. Some unknown parameters of the PDE. This picture is from Cho. I will show you at the end the paper. But when we get the data, already from the data, we have uncertainty. So if we go back to Laplace and the scientists in the 19th century, they say that if an intellect had all the information they need in order to write down a mathematical model, a PDE, then nothing is uncertain in the future. So basically, as long as I have a PDE model, I can do whatever I would like. There is no uncertainty. But it's not the case. So that's why we are here. So what we get is this. We have our observation, yi, and we have a forward map, g theta. This g theta arises from the solution of a PDE, and then we have a space, we discretize a space, and the solutions of the PDE, we evaluate it at a discrete point, which we randomly picked from our space. We do the evaluation there at this point of our PDE, of the solution of our PDE. Then we add some noise. In our case, we add Gaussian noise, and then we have our observations. So basically, what is it? What is this G forward operator? This G theta is just a collection of regression. So, but this time, theta, we are in infinite dimensional space. So theta is, so this forward operator is indexed by the infinite dimensional parameter theta. So, so in inverse problems, in inverse problems, what actually we have a parameter space, and we are going to the solution space, and now we want to recover theta, our parameter, which is connected with our PDE. So the PDEs that we are using, I mean, examples that, like from PDEs that are connected with our forward map, is elliptic PDEs, like when we have like a groundwater flow, how we are doing oil mining. These are described, all these problems are described by an elliptic PDE. So if, for example, you have like, you want to get like an image of the torso from some medical examination, what you have to do is like an X-ray transformers, and all this described by transport PDEs. And then at the end, we have time evolution equations, like the Navier-Stokes, like the heat, the wave equation. So, and this, on top we have like, apart from the parameter, the unknown parameter that we want to estimate, we have also the time. In our cases, in our case, we are focused on elliptic PDEs. We will not talk about Navier-Stokes or wave or heat equations, but I mean, we are working on Navier-Stokes recently, and because Navier-Stokes arises also from data assimilation, because you have all your observations, but you have also the time in your observations. So Navier-Stokes is like what you are using for data assimilation. Let's see more precisely the models that we are using in PD. A model, that PD model, which we use extensively, and actually how this work started is with Darcy, the Darcy flow, which is an elliptic PD. And what we have here, we have the divergent operator, we have a parameter here, g theta, then we have the gradient of u and the source function f. We have some boundary conditions. And then what we want to do from these observations, we want to infer theta. Another example is like Schrödinger equations. So we have this calligraphic, which is the Laplacian operator. Again, we have this, this function here, g theta, which we want to recover. And then we have some boundary conditions. And again, we want to recover here g theta. But okay, here what you have to like to understand that the forward map g theta is what it will give us the solution of the PDE, is the solution of the PDE. And something which is important to understand here that if you see here our PDE is this operator is linear, but the non-linearity arises from the forward map, because sometimes you might have like a PDE, but you don't know the solution. We don't have analytic forms from this solution of the PDEs. And when you want to do the inverse problem, it's really difficult. I mean, sometimes it's like, so that's why we are trying to do statistics in order to uncover this forward map. And why it is difficult? Here you see an example. What we have, different G's. Like we have like a Gaussian process. We draw priors, and then we simulated G1, this coefficient, and G2, and we see that it's different. But once we are trying to do the solution, like if we want to see the solution, we see that it's quite similar. So at the end, if I have my PDE, and I have the solution of my PDE, I'm not sure from which this parameter we used in order to get the solution. So this makes it really hard to do the inverse problem and then be sure that we find the right the right parameter. So, and then we have Stewart, Andrew Stewart, 2010. It started all this direction, in this research direction, who studied Bayesian inverse problems that which are arising from PDEs. And then basically, and then it's got quite influential. A lot of researchers are working on this direction recently, and it's getting really a lot of attention the last decade. What we have, so now what we are trying to solve, we are trying to solve this nonlinear problem using Bayesian statistics. Okay, so for example, you might, as a statistician, you might think of the least squares fit function and the log likelihood, which is just you get the sum of the squares of the difference of what you observe and what you would like and what you have from the solution of your PDE. But then, because G theta is nonlinear, it's really difficult to solve these problems. To use an optimization method to solve this problem is quite difficult. So now what Stewart suggested is, okay, let's put some prior and let's follow the Bayesian approach. And then actually, when we assume that our prior starts, we have a prior from a Gaussian process, then the posterior distribution is proportional because it is Gaussian, will be proportional to exponential of our least squares fit. And then what he said, once I have a mismatch, the prior and the model, because what it is important is when we model the prior should somehow match and aligns the properties of our PDE model. So once I have a mismatch here, I penalize, and then, okay, here we penalize in some reproducing kernel Hilbert space, and then we have, and then we solve it through a posterior distribution. And then what we can do, we can do Markov chain methods, and then we can infer theta using MCMC. Again, here, why we want to use this problem, because we don't use analytically the inverse problem. We using the Bayesian statistics and using this, we don't have to explicitly say what it is the nonlinear inverse. Okay, and then what we can do, we know from statistics and mathematical statistics when we study, that okay, I can find the map estimation, and then this coincides with a penalized least square. And then again, avoiding all these optimization problems, we can calculate, and then we can have a form for our expectation for our parameter given the data that we get. Although we have this one, and we might do MCMC as statisticians, we are interested of different questions to ask. The first question statisticians ask, once we have a parameter estimation, if it is statistical consistent. So basically what we want to ask is if we reliably solve this problem, this inverse problem. If like posterior distribution, once I calculate the posterior distribution, do I reliably solve the inverse problem? Do we recover the ground truth from the data that we get? And basically we want to understand how our parameter contracts, the rate that our parameter contracts around the ground truth. The second question comes from the computational perspective. Okay, I have my posterior distribution, and I want now to go to higher dimensions. And then what I can observe that our this difference between yi and my forward operator, this might not be even long concave. I mean, and then it's really difficult to compute to compute it efficiently. And then the last step is what we want to do is uncertainty quantification. When we have posterior distributions and we construct some error bars, does these error bars give reliable confidence regions in order to say something meaningful on theta? So this is the questions that in these types of problems we like to answer. So all the answers to all these questions are really based on the analytical properties of our PDE. So the PDEs, how the properties of our PDEs are really connected with answering contraction rate, getting credible intervals, and computationally. And then, because all these properties of the PDE is encoded in this forward map. And then what we have to do, from Bayesian, we have to linearize this forward map. So we need to linearize this forward map, which is given by the first derivative evaluated at theta naught. And we need to know the regularities, what regularities assumption we put on our prior, on our truth, and the prior, because this, we need to align the properties of our PDE and the properties that we put on our prior. So basically, the first result is the posterior consistency, and then what we say that we are able to prove this type of limits, that our parameter contracts at a rate of epsilon n around the ground truth, given I have the posterior. And once I have this limit, I can also prove that I have convergence rate for our expectation. And until now, a lot of works have been done in this direction, and a lot of work has been done by Nickel, and he worked on non-abelian X-rays, Calderon, Darcy problem, parabolic Schrödinger equation. Recently also Agapeu and Wang had some recent results in that regard. And the best, okay, we have, okay, the rate here that we have, it's, in this K, it also depends on the dimension of our discretization, how we discretize. It's hidden here. I just wanted to show that when we have the logarithmic and then we have n. Again, all these rates and all these contraction rates really depend, boil down to a key analytical property of our PDE. And this one is we want to have stability, our solutions are stable enough. Because what we can do with this estimate, that is the stability estimate, it says that, okay, once I have something for our forward operator, then I can say something for the parameter itself. And this is an important property for the PDEs, and in order to have and for our linearized operator. And then what we are doing, we have this, we have something for the forward operators, and then we can say something for the inverse problem. But we don't directly solve the inverse problem. We are using these estimates and then the stability estimates from the analytical part of the PDE in order to go back using statistics, using Bayesian statistics, and say something about our parameter of estimation. And then the last question, okay, I will not say anything about computationally and the MCMC algorithms. I will focus only on contraction rates and uncertainty quantification. And then basically, once we have like, okay, we have contraction rates, but having contraction rates is not enough. So now, once I have my contraction rates, what can I say for credible sets? Can I have like, I mean, using my posterior and some credible sets, do I have exact coverage at a nominal level? Or like my parameter belongs to this credible set and converges at a nominal level? This question can be answered by Bernstein von Mises. So Bernstein von Mises, long time ago, said that, okay, my posterior distribution can be approximately by the normal distribution as n goes to infinity. We can see it in a total variation distance sense here, and with covariance operator, the Fisher information. But here we need to be sure and that the Fisher information is invertible. All of these are okay as long as we are in a fixed dimension, as long as we are in a finite dimension space. Once we are moving like the parameter spaces once our parameter space is on infinite dimension, then this breaks down. So we don't have any more this Bernstein von Mises theorem, and so we can say that our posterior is approximately Gaussian in the limit. But now, what we are trying to do, we are trying to adjust, and then they say, okay, maybe we don't have the Bernstein von Mises theorem, but maybe we understand convergence in a weak sense. And now what I'm doing, I don't want to do some inference for theta, but some linear functionals, psi theta. Okay, and now the question that we are asking is, does the cylindrical posterior satisfy the Bernstein von Mises? Once I pass and I project to a linear space, and then I'm just like have these linear functionals, can we say now something about the Bernstein von Mises or Gaussian approximation? So what we found is like we need to go beyond Bernstein von Mises, and what we saw, and this picture will arise later, but even if we don't have Bernstein von Mises theorem, even if we don't, but we can say still something meaningful for our posterior. So basically here what we have, we draw like the posterior using a specific example of a PDE. I will show you at the end. It's a little bit technical and it's tailored exactly to not satisfy all the good properties, and still that we get like some Gaussian approximation when we do the MCMC draws. Okay, and then we have also some intervals for our estimation. So these pictures, it says us, okay, we have to go beyond. So what's the previous, let's see, let's take a step back and see what has been done all in the past in the literature. So one really important thing like to understand for the Bernstein von Mises is that we have this Fisher information to invert. When we go to the infinite dimension space, we are dealing now with similar, and we call it information operator. And it really depends on the adjoint of the derivative of our forward map evaluated at theta naught. This is an important, the adjoint operator is very important because apart for giving us something, the covariance operator in the infinite dimensions, we gain a lot of information about the curvature around theta naught. So this is another important step because what we gain, we see the geometry around the truth. This type of already in the linear inverse problem back on 2011 by Van der Waal and Knapping, they have these results in infinite dimension, but for linear inverse problems. But again, what is really important here, like when we use like a sequence representation for our prior, is not readily available. That we will have like a characterization of this of our adjoint operator because of the non-linearity of our forward map. Now Monard and Nickel and Patterson 2021 showed that I mean we can have a Bernstein von Mises theorem for the Schrödinger equations. Once I have like what I have a smooth like a smooth true parameter, and my psi, the test functionals belong to the range of the adjoint operator, then we can have a Bernstein von Mises theorem. So basically what they say is once my test functionals belong to the range of the adjoint operator, then I should expect Bernstein von Mises theorem. But in order to test that if a psi belongs to the range of the adjoint operator, wasn't possible in when we have like conductivity estimations in Darcy flow problem. So now what we are trying to do is to understand that okay, even if we don't, if our size does not belong to the adjoint operator, still we can have something meaningful, even if it's not the Bernstein von Mises. And then, of course, we want to understand coverage. Recently, there is this work by Van der Waal and Kers that they study similar problem, but they use a different method. They try to linearize a map, and then they linearize a map. This and the non-linearity problem translates to a linear problem. It's a recent work by Van der Waal and Botond and Kers. It's different to our approach because we don't try to linearize the non-linear problem, but rather work with the smoothness and the smooth scales on prior. We don't do any discretization of the parameter space, and still we like to have some Gaussian approximation of our posterior distribution. So here, now I will show you what we get from some properties, frequentist properties, if we assume that theta comes from a Gaussian process. So again, let's see again our PDE. I have a divergent, an operator. I have, I have the divergent operator. I have gamma naught, the parameter of our PDE that I want to estimate, and then I have the gradient operator, some source functions here, some boundary condition. The source function I assume to be smooth enough, and it's known. And then we have the domain for our PDE with smooth boundaries. Okay, now gamma, which is our parameter to be estimated, belongs to some Sobolev space, and the smoothness is strictly larger than 1 plus d half. And then all these assumptions we need And then on top we need like our parameter to be bounded. And these properties actually implies that I will have existence of unique existence of our PD. And this is important because after all we are trying to understand like we need to have a uniqueness solution because we want to invert. So now in the beginning I showed you that we have a random design, so we have a forward operator and then we add some noise. But here I will do the estimates, and what we have done in the paper we can find it in the random design, but here I will use the continuous the continuous model because it's easier to present the estimates. So basically what we have is we have like our observation, we have the solutions of the PDs that are of our PD, which arise when we use this parameter for conductivity, and then we add some white noise. And then what we want to recover gamma naught, which belongs to a Sobolev space with smoothness beta. And then we have some, again, constraints which come from the PD in order to have a strong solution. And then like this, the Darcy flow is important like in oil mining, and there are some applications like by Stewart in 2010. It's this very influential paper. And now what we want to do, we want to put some prior on our parameter space. So what we are using Gaussian processes. Okay, and then what we say that our parameter is Gaussian, and with covariance operator lambda, this you think of it as a Laplace operator, and we have some smooth scale A. Now, because we want what we want to do in order to ensure that we have the solutions of our PD is unique, we need to be careful on our parameter. So what we are doing, we have a link. We link our parameter with a function phi, and now we have this phi capital in order to satisfy all these good properties that I told you earlier that we need to have. We need to have some positive, strictly positive conductivity parameter, and to be bounded by gamma min. Usually what we are, not in practice, what we are using is the exponential. Like, I mean, you can take the exponential of theta, and then all this works really fine. And now, our what we are doing, we apply on our parameter. We scale our parameter by tau n, and this tau n, it can be either 1, but if we want to have faster rates, and it's something that we couldn't avoid, like in the literature, everyone in the literature uses it. It's like we have some polynomial decay in n, because then we get like some faster rates. And then what we have, alpha, here is the smoothness of our prior, and beta, keep in mind that alpha is the smoothness of our prior, and beta is the smoothness of our truth. And actually what we are playing, and like what we are doing different with other works in this, we play with the smoothness scales and the Hilbert scales. There is this theorem really a long time ago, and interpolation scales between in order to get our result. So the first result that we get, and now we are focusing, again, this result is for the continuous model, but is really, we have a similar theorem for the random design scheme for the observations. So basically here what we say, there are some quantities that I will explain them in the moment, and we have Sn and Bn. This is the bias of our of our approximated posterior, and Cn is the variance. And then we have some sequences, height psi hat n, we'll show in a moment. And first, we need to assume that our linearization, the errors that come from the linearization, is of order epsilon n squared. And this is the difference, because before in the literature, Richard Nicol used like that the error is of order 1, and also for the case, in our case, for the random design scheme, also we use the same order. But if we have this order, epsilon n, which relaxes what has been done until now, we have this penalty here. But I mean, we expect this to be satisfied as long as my posterior is it puts mass where it is exponentially concentrated. So as long as I have this property, then it's not something really hard. It's not something crazy to ask like that. We have this epsilon n squared for our linearization error. The difficult part also, in our case in the random design, apart from the linearization of our forward map using this, doing this linearization, is the discretization error, how discretize the space. And then what we find, that up to a bias correction term, Bn over Sn, our functional will be normally distributed in the long, will be normally distributed. But what we have to do now is, we have this result, but we have it like up to a bias correction. So in order to be able to say something, we need to control this bias term, and this is like where the difficulties come. So basically, again, I will just describe the quantities that we use. First of all, we have like what we use, and it's different than the other works, is how we perturb our vectors, and we perturbed in a way that the adjoint operator always, the inversion of the adjoint operator exists. And always, like, I mean, even if the psi, the test functional, does not belong to this range, still I can have something meaningful. So this perturbation is not, is a little bit different. And then what we are doing here is like the asymptotic variance. By perturbing in this direction, we have some bias as well, and then we have the linearization of our operator, and the worst case, and the usual approach that in this type of problems that we want to prove a Bernstein-von-Mises theorem is the local asymptotic normality of our posterior. So we do this approximation. So again, what we need, once all this Bernstein-von-Mises theory fails because of all these not nice properties, that our properties are not satisfied, even if I don't have an efficient estimator, still I can have some conservative coverage. So, but again, in order to have this conservative coverage, we need to play with the smoothness of our prior and our truth. And a crucial thing is that if you see here how we define, a crucial thing is that in linear case it's easy, is how how these two operators, we cannot diagonalize them at the same time. So, and this is a problem. In linearized case, it is okay, but assuming a perturbation in our case, and we don't do direct diagonalization of these two operators. This is another thing that we avoid doing. So basically, again, even if we have this, even if this is the case, and the prior still does not belong in the range, what we can do, we can use an extra assumption in order to cover for these problems, and this is Armstrong injectivity on our linearized forward map. And we say this is a little bit different, that because we are using the smooth scales delta S, and then in order to have some freedom how we will play with the smoothness, and that they are always, even when we go to the worst direction, our posterior will always focuses on the direction where we have mass from the prior. And here is the result. And basically in that result, what we have to prove actually in order to have this Gaussian approximation is this bias correction term that I showed you earlier to be of order 1. Because as long as this order is of 1, then what we can do is we can control this bias correction term in such a way that I will have our functionals will converge in a Gaussian distribution, and this will be our covariance operator now. And this will be of order 1. Again, if our functionals belong to the range of the adjoint operator, then I can recover the Bernstein-von Mises theorem. I will not focus on the approximation idea, but what we have, to understand is the difficulty and the challenge part is when we are trying to say something about the injectivity of our adjoint operator, which is important because it's our covariance operator. They are not, we cannot diagonalize them at the same time with the operator which comes from the prior. And because of that, another thing which arises that our functionals does not belong to the range. So if it does not belong to the range, again, Bernstein-von Mises fails. So basically, we are able to have, like for the Darcy flow, that's something which was not known in the literature in case we have like test functionals that belong to the range, is we can have a conservative coverage. So basically what we said that our functionals belong to the interval. We have exact coverage in case the psi belongs to the range, and we have like conservative coverage when the psi does not belong to the range. And again, what we assume here, something really important to understand is, and it's contradictory, when we want to have like contraction rates, we have to assume like smoothness in both prior and the truth. But in the case, what is like really contradictory is like in order to get conservative coverage, we need to assume another smooth prior. So, and this is a little bit contradictory, but this is, you have to believe me. Let's go back to the example that I promised in the beginning that does not work, and it's tailored on that direction. So what we use here, we use some functionals here, which is the BAM function. If you see it, it is like say infinity, but this psi, the specific psi, no, sorry, but this specific psi does not belong to the range of our adjoint operator. And then again, the example that we use here, it is a Darcy, it is the Darcy problem, and then when f is given by this quantity, we have a given analytic form. And then for this form, we can say that the true is equal to 0. So gamma naught, which is the solution, it is like what we had, like the parameter, sorry, not the solution, the parameter of our PD is 1, because if you remember, we use the link function in order to assume all good properties for our PD, and it is we exponentiate the true parameter. And actually, this is the case because in pattern 9 in 2022, assume that this is not possible, but using this example, it's possible to have Gaussian approximation. Maybe not a Bernstein von Mises, but still we can have something nice. And this is like the MCMC draws for this functional. And then we see that they are concentrated around 0. And with different, like, here we use like 10,000 samples. And this is the mass, like how we discretize our space, the grid of our PD. Okay, so what we gained, again, what I showed you until now was that in cases that we are in infinite dimensional space, and even if the Bernstein von Mises theorem fails, and even we cannot have the optimal rates, which we might not have the optimal rates, we still have a Gaussian approximation up to a correction term, and the rate that depends on the smoothness of the prior and the truth. And if we assume that we have enough smooth truth and prior, we can have even the square root of n rates, which is the optimal. But again, the contradiction comes for the coverage. We need to undersmooth the prior, so in order to have a good coverage. And this, I show you this for the continuous model, the white noise model, but we can have the same results if we have a random design. So, which is more difficult because we have also the discretization of the space, apart from the discretization, but from the error which comes from the linearization of our operator, we have also the discretization error. Okay, so until now, we assumed that we have a well-specified model. So basically what I found is what I supposed to find, but in practice it's not the case. So in practice, I mean, we don't know. I mean, if we are using the correct parameter for our estimation. And so we need to do something to accommodate also model specification, misspecification. So this is something from the with real data. So basically, here we have a transducer. So it's like we want to say something about. Here you can think of it like the arteries on the arteries, and then what we are doing, we get the results. Like first, this is we have some ultrasound. We get some waves, then we add some Fourier here, we get the frequency, and then we have some dispersion curve. And now at this part, it comes like the non-inverse problem, the non-linear inverse problem. We want to see the curve from which actually PD arises. And then what we are solving is this step. And this again is the source by Roy with real data from 2021. So the statistician, we want to solve this problem. So, and why we want to do misspecification is, okay, there are many sources in order that counts for a certainty. First of all, our data, we have noisy data. Then what we have is a PD, but we don't know. As I showed you in the beginning, I might use different parameter and still have the same solution. And then what we have, and that, what we are doing, then the researcher says, okay, I will restrict to this model, and does not change, the posterior from which they draw inference. So we need to account also for misspecification. So how we will count this misspecification? One is to use this band limit prior. So what we are doing here, we have this sequence, this representation sequence, and then we say here gamma L is some weights, psi L is our orthonormal basis we choose, and then basically the prior depends on how we choose ZL. So if ZL is normal, then I have a Gaussian process as a prior. But now what we are assuming, we have this bandwidth, this band limit, because we have we concentrate it in this interval, in the M ball, and you think of it as an L2 norm, the balls. Okay, and then the second way that we can use in order to count for misspecification is to use this tempered posterior. So basically what we are doing, we are adding a parameter here in front of the likelihood, and then what we are trying to do is we allow to get the same rates as with the Gaussian likelihood, but we have to assume this time that the error of our discretization or the errors of our approximation is at most sub-exponential. And what we have a contraction theorem. We simplified it here. Okay. So basically what we say, we have a theta star. Theta star is the minimizer of this functional. So basically theta star is something that minimizes the distance, the L2 distance between what is the truth and what we get. And basically what we have is this contraction rate, how far is our forward map. Again, what we have, the models, the data are given by a forward map, F naught, plus some noise, and we have the errors that sub-exponential tails. And then what we have a contraction rate of this order, and beta is the smoothness of our truth. And again, the difficulty here is we don't take for granted that such a minimizer exists. In the work was done by Van der Waal and Klein, they assumed that such a minimizer exists, and we have a convexity. Because what we now assume that the image of f of our operator is not convex, so we don't know that a minimizer will exist. So again, we have this contraction rate, but this result depends on the signal-to-noise ratio of the problem, and this is something that we are still studying. And basically here it is how we prove that the existence of this minimizer. We use standard arguments in functional analysis, and once we restrict to a weakly compact set in L2, and we use a weak convergence subsequence, we can have this this existence of the minimizer. Okay. And now I would like to discuss some possible discussions that some possible extensions of how to use what we have done until now in some other setting. And the first thing that we have also, another thing that we have to count on is non-Gaussian priors. So because Gaussian priors is when we want to estimate a spatially inhomogeneous coefficient, this type of coefficient belongs to a Base of space, and then like when we have the base of space, the irregularities are higher than in assuming a Sobolev space. And recently, the work by Arapiu and Wang, they saw they saw contraction rates for the elliptic PDEs, and we can use their approach. So basically, what we have for our prior, we define this sequence, this series, and again, gamma L is a weight. Sorry, here is the mistake, is L, not K. And we have the weights. We have some bases and some randomness which come from these variables ZL, and depending on what we assume for these variables, if they are normal or Laplace or whatever, then we have the appropriate prior. So for example, if ZL is normal, then we have a Gaussian prior. But now what we want to do is to assume a Laplace prior in order to cover the case of non-Gaussianity. And again, now this is this like the elliptic inverse problem are especially the contraction, not especially, only the contraction rate theory is really well understood and developed by the recent work of Arapiu, that they encounter different priors in base of space, and also Giordano and Nickel, they had this work. They assumed wavelet basis for their priors. And now, what they did, Arapiu in 2021, at some point when we have like in Bernstein hormesis, when we have this perturbation for the posterior around our ground truth, we need to deal with a Radon-Nikodym derivative under some shift. So basically, they have this expression, this exponential for like when we have like this form for our priors. And then basically what it says that the prior, once we have this Radon-Nikodym derivative, they could prove that the prior can be can come from like exponential tailed distribution. And actually using this result, what we want to do is there is some connection between the base of space and the Laplace prior. So basically we can exploit the alpha smoothness of Laplace prior, and basically to be in the same space, and to have the space absolute continuous shift, even if we use the Gaussians with the Laplace priors, using the result. And we can have this lemma using the result. And so basically it's, again, we have this, we can have this Radon-Nikodym derivative. And finally, okay, I will sum up. Then we can have a uniform control for between the Radon-Nikodym derivative of a Laplace prior and the Gaussian prior. And then basically what we have done in the Gaussian case follows, we can recycle them for the, in case that we don't have Gaussian priors, for the Laplace priors. And again, this is not surprising because in spatial case, the base of space is a subspace of the Sobolev under this regularity condition, smoothness. And okay, we have done like coverage. We have done like, we are dealing with misspecification. We have seen this misspecification case, but now we want to understand like how we can adaptively choose this tempered parameter for the misspecification case, which is not something trivial, and then what we can say about the frequent coverage in that case. And then we want to get more rigorous algorithmic result on sampling complexity, and finally to do some contraction rates and for Navier-Stokes. And here are some references for this work, it's a lot. No, it's not only this one. It's like it's really a lot of researcher work on this direction. But some of this I pointed out here. I guess you will see them once the slides are shared. And yeah, I think that's it.
Time for a few questions. Sorry, thank you very much for your very deep talk. I was curious about the Bernstein-von Mises theorem in the linear case. That is, maybe you mentioned it, but they exist in a functional. They are stated in a functional way. Okay.
Yes, there exist. There is a.
For the linear case, they exist. Okay.
Yes, by Vardova.
Okay. Here it's much more complicated,
yes.
but the bias is terrible.
Yeah.
That is the non-commuting of these two operators is terrible.
It's terrible.
Completely terrible.
I totally agree. That's why we wanted to avoid it.
Okay, thank you very much.
So in your case, when you looked at the functional, I don't know if I missed, but do you adapt to the known smoothness of your function? I think it's beta or not?
Sorry, the functionals here?
Yeah, so before, in a well-specified model, when you were looking at the BVM, I think you had, so alpha was prior smoothness, and beta was the actual smoothness of the function?
Yes, sir.
Can you adapt to this, to beta if it's unknown?
To adapt if beta is unknown? No. No. Okay, this is a difficult question. I mean, to adapt, no.
Sorry, in linear cases.
In linear cases,
no.
In linear cases, is understood. You know that. But in the non-linear case, no. I mean, it's quite difficult actually. Yes, I don't know. I mean.
Okay, there is no more question. Thank you again.